let's take a look at families of functions. Now, as we explore these function families, I want you to keep some questions in mind. You might even want to jot down answers to these questions or any ideas you come across. Here are some prompts to think about. What characteristics are unique to this family? So what makes this family different, special, noticeable? How would you spot this family in future lessons? What would you look for? What parts of the graph does this family have or not have? And why does that make sense? So if there is something this graph doesn't have, why would it make sense for it not to have it? If this graph does have something in particular, why is it making sense that it does? What characteristics or patterns do you see that every family has? There are some things that all of these have in common. Can you figure out what they are? And what do you not understand about anything? So as you're looking at these families, jot down anything that you want to ask about. Why is this doing this? Why is it behaving that way? Why is that the answer? Now, to make this easier to work through, I will have screens that show each family title so that if you want to revisit later but only look at a certain family, you can shift the video and only play the part that you need. So here we go. The linear family. Now, the linear family, let's take a look at this with a sample. Y equals negative 4x plus 3 is its rule. Now, one of the questions we ask is what values could you choose for x? So what could you plug in here to this rule? Well, since this rule is just saying take the number I pick for x, multiply it by negative 4, and add 3. There's really nothing I couldn't use. I could pick any number I want, positive, negative, fraction, decimal, anything, and I could multiply by negative 4 and add 3. And so because of that, since I could plug any kind of number in for x, I could make any answer come out for y. So what can I choose for x? Anything. What could I get for y? Anything. So then in order to do this, I went over to my table. Since I'm allowed to choose anything for x, I chose the 7 numbers that would be the easiest. 3 negative numbers, easy to work with, 0, and 3 positive numbers that are easy to work with. And you notice that they're all in a pattern. That's on purpose. Helps you see the pattern in the y column. So then I plugged each number into the rule and got the answer for y. And then I took this table and plotted each x, y column as a coordinate and made my graph. And then I used Desmos to help me find some of these things. So when something was looking like a fraction, like in this case the x-intercept, I put the rule into Desmos and looked at the graph and used it to assist me. So I found that the x-intercept was at 3/4, 0. The y-intercept was at 0, 3. Now, a vertex is where it changes direction. This one doesn't, so it has no vertex. As far as a line of symmetry, I suppose I could find one maybe kind of diagonally here that cuts it into an equal half, so a perpendicular. But in true line of symmetry, the way we think about it, this one really doesn't have one. It has no asymptotes. And the thing I noted was, well, it's a line, so it has a constant rate of change. I noticed that as I read left to right, this line is going down 4 squares and then right 1 square. And then the next is down 4, right 1, down 4, right 1. So that's our linear family. The absolute value family. So remember, absolute value calculates distance, so it makes things positive. So when I plug something into absolute value bars, it gives me the positive answer coming out. So when I think about what can I plug in for x, well, I'm supposed to take what I plug in for x, subtract 2, make the answer positive if it isn't already, and then add 5. Well, there's no number in this world that I'm not allowed to subtract 2, make positive, or add 5. So I could choose anything I want. Now, the problem is, though, all of my answers for y, because I'm going to subtract 2 and make it positive, then the absolute value bars are going to produce a positive answer. In fact, the smallest number that part of the rule, this part here with the bars, could produce is 0. And then I'm going to add 5 to whatever it is. Well, that means I'm going to get no negative numbers whatsoever for y, like none. There'll be no negatives. And since the bars could only go down as far as 0 and never any lower, then by adding 5 means all of the answers I'm going to get are going to have to be 5 and up. So anything greater than or equal to 5. So I went ahead and I picked some various numbers. Now you notice I didn't pick the same numbers as the linear family. So part of what you might want to figure out is why these 7 numbers and not the same 7 as linear. And I got my y answers and I went ahead and graphed them and I got this interesting shape. This particular graph had no x-intercepts. It never crosses. It has a y-intercept at 0, 7. It has a vertex at 2, 5. A vertex. And it actually has a line of symmetry. If I go to the x equals 2 graph line, I can cut this V shape into perfect halves. It doesn't have any asymptotes. It is a V shape, which is interesting. I notice the left side is going down 1 square, right 1 square, but then the right side of it's going up 1 square, right 1 square. Well, that's intriguing. It's almost like a bent line. And I notice that this V is opening up. Something tells me there's a way to make these V shapes be upside down. So that's an interesting thing to think about. But this one opens up. The cubic family. Now a cubic family means that it has x cubed in it. So here's a sample rule. Now this rule says take my number for x, cube it, then subtract that number from the answer, and then add 2. Well, applying powers, subtraction, and addition have no restrictions. I can do that to anything and everybody I want. So I can choose anything I want for x. And because when you cube, you can get both positive and negative answers, that means I could make anything come out for y. So it's all fair game. So for my table, I chose the same 7 as the linear. And when I got the table, I got 2, 2, 2 here. And I didn't think this graph went straight sideways. So then I tried plugging in positive 1/2 and negative 1/2 just to see what those answers were going to be in between all these 2's. And based on that, and then tossing this into Desmos so I could see it visually, I got this nifty little bumpy curve here. And I used Desmos to help me find that x-intercept. It was at around negative 1.5, 0. The y-intercept was at 0, 2. Using Desmos, there are 2 vertices here, 2 like bumps in this graph. And so I used Desmos to find them. One of them was at negative 0.6, 2.4, and the other was at about positive 0.6, 1.6. Those are rounded, of course, but close enough. Now, this thing has no line of symmetry. No matter how I cut it, I'm not going to make equal halves, and it doesn't have an asymptote. It does look, though, as though the graph makes some kind of turn right here at 0, 2. It's like it's going up, and it makes a hill, and it's sort of arcing like this. And then after 0, 2, it arcs a slightly different way, and then heads in a different direction. So 0, 2 is not really a vertex, because it didn't change direction. It just did like a turning point. It changed at that point. I also noticed there's no consistent spacing between the points. So unlike the last 2, there's really no going up 5 and right 1. There's no consistent spacing, but it did make a really cool curve. Now let's look at the cube root family. A cube root, which we know means a number that multiplied by itself 3 times produces an answer, can be used for calculations. So this one, I'm going to add 1 to my x, then do the cube root of the answer, and then subtract 3. Well, cube root has no restrictions. I can put anything I want in a cube root, positive, negative, whatever. So that means I can put in anything for x. And because cube root produces positives, negatives, and everything, I could get anything I want for y. So since I didn't see any reason to choose differently, I picked the usual 7 values. and I plugged them into a calculator and I got some wacky decimals, which I rounded to the tenths. And when I graphed it, I noticed I was getting this kind of flat, swooshy thing. And so I was curious, would this right side ever cross the x-axis? I mean, it says I could get anything for y, so I'd assume that eventually I'm going to get positive y answers. So using Desmos, I was able to discover it crossed the x-axis at 26,0. So it eventually starts getting to positive y's. It's just going to take a really long time. The y-intercept was at 0, -2. There is no vertex because there is no place where it's changing direction. There are no lines of symmetry or asymptotes either. Might seem like it's got an asymptote, but we do know it eventually crosses the axis, so it is sort of heading in this upward direction, and that means that this left side's doing the same thing. It will eventually get down to where y is -50 or something like that. All I really could see is that, especially in Desmos, it felt like -1, -3 was some kind of a turning point where it was sort of swooshing up from kind of like an underhand curve, and then it switched to like an overhand curve. So there's a weird kind of turning point. Again, no consistent spacing, just lots of weird decimals. Next up is the quadratic family, one of my favorites. Now, quadratic means it has squared in it. So this sample rule says that I should take my x, square it, make the answer negative, add twice the x to it, and then subtract 4. Well, I can put anything I want in for that. But then I began to wonder, when you square a number, it only comes out positive. So that could cause some issues here. And so I actually got the answer to this, what I get for y, by looking at Desmos, because I'm like, I don't even know. So I looked, and I noticed that the entire graph stayed from the y = -3 line and down. So then I built my table. I noticed on Desmos my vertex was at 1, -3, so I made the vertex the center of my table. Makes it easier, because then I get some nice answers. I had noticed this particular quadratic did not have any x-intercepts, had a y-intercept at 0, -4, a vertex at 1, -3, and I noticed that if I put a line through where x = 1, that made a symmetry for the quadratic. No asymptotes. It is a parabola, yay! And it has a maximum. This thing reaches a highest y of -3. And I did notice some kind of symmetry repetition going on in that table, where each number on either side of that vertex was repeating. That was kind of cool and unique. The square root are also called root or radical family. Now, with a square root, I know square roots can't be done on negative numbers. So that means that I can't plug in anything here for x that would make that answer after subtracting 4 be a negative. Well, that means that I can only pick x's from 4 and up. Because like if I put in 3 for x, I'd get a -1 under the square root, and that's bad. I can't do that. So I had to pick numbers from 4 and up, and that dictated my table. I went 4, 5, 6, and up. And then if I plug in 4, I got 1 for y. Well, if 4 is the smallest I could get for x, then that 1 turns out to be the smallest I can get for y. So my y's are going 1 and up. Weird decimals. Kind of a cool graph. It had no x-intercepts, no y-intercepts, no vertex, because it's not changing direction, no line of symmetry, and no asymptote. It had nothing. But it did have a starting point, which is kind of bizarre. This thing just sort of started in the middle of nowhere and like zoomed off. And when I turned the graph around, it actually looked like half of a sideways parabola, which was kind of neat. Having just done the quadratics, it was like, hey, that looks like half a parabola sideways. And again, no consistent spacing or predictability in its change. The exponential family. Now, exponential functions have x as the exponent. And it turns out that you can plug any number you want in as an exponent. Try it on a calculator and you'll see. Put in decimals, put in negatives, try fractions. You'll get answers for y. You'll get some very strange answers, but you'll still get answers. So not knowing what this was going to look like, I tossed it into Desmos, and I noticed that this graph stayed above -3, but it never seemed to get to -3. Like I zoomed and dragged and everything, and it never seemed to get there. So it meant that y was going to be greater than -3. And so I plugged in some sample values, and I was starting to get some really crazy fractions. So I graphed it, and using Desmos, I discovered that the x-intercept was at about 1.60. My graph wasn't drawn super accurate here, but hey, it's a hand graph. Give me a break. The y-intercept was at 0, -2. This has no vertex. There is no place where it changes direction, really. No line of symmetry, but it has an asymptote. There is that imaginary line of y equals -3, where the graph seems to get closer and closer and closer, but never actually touches. Now, there's no consistent spacing. It looks like it's getting flat to the left and almost vertical to the right, but it never gets perfectly vertical, because perfectly vertical would mean I plug in a value for x and get multiple answers for y, and that's not happening here. But it is getting really big really quick on the right. Last but not least, we have the inverse family. Now, the inverse family puts x in the denominator. Now, denominators are pretty forgiving. There's only one denominator you're not allowed to have, and that is 0. So when I look at this, I think to myself, well, I could plug in anything I want for x so long as I don't make 0. So what's the only number that would make that denominator 0? That's 2. So I can choose any value for x I want, positive, negative, fraction, decimal. I just can't use 2. It's like having an allergy. This function is allergic to 2. It can do anything but. Now, when I look at this problem, I have a fraction of 1 divided by something. If I take one whole and I divide it by anything, I'm always going to get something. Something tiny, something big, but I'm always going to get something. That means that the fraction part of this rule would never equal 0. I can't take one whole thing, divide it by some amount, and get nothing. So if I'm never going to get 0 for the fraction, then I'm never going to get 5 as an answer for y. So anything but 5 is going to come out. So I picked some different x values using that bad 2 as sort of my anchor. And I noticed I got some very strange answers. So then I tried a few more. I tried x is -4 just to see what would happen way out there. And I tried 1.5, which is between 1 and that bad 2. And then I tried 2.5. And so I went to Desmos and I discovered it had an x-intercept right over here of 1.8, 0. It had a y-intercept of 0, 4.5 roughly. This thing has no vertex. It really has no line of symmetry, but it has 2 asymptotes. How cool is that? One where x is 2 and another where y is 5. This graph has 2 parts. That makes it special. All the other graphs were one-piece graphs. This is a 2-piece graph. So there are 2 branches to this graph. And while each branch looks exponential, it's not, but it really does look like it could be related. And that 2 asymptotes is just so cool. So this completes our families of functions.